What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit. This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers. The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand. (15 to 20% of zinc goes into making alloys like brass and die casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800,000,000 tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile.
Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
Every second, 30 million microchips are manufactured worldwide. Smartphones, computers, cars, satellites, everything runs on one element. It's hiding in ordinary sand beneath your feet, but after an incredible transformation, it becomes the brain of digital civilization. That's silicon, the second most abundant element on Earth. Yet getting it pure is harder than extracting gold. You'll discover how sand is melted at temperatures hotter than the sun's surface, why a single gram of impurities can destroy a million chips, and how they create a material that's 99.999999999% pure. Watch till the end, because the finale reveals how a handful of sand gives birth to humanity's future. The story of silicon began in 1824 when Swedish chemist Jan Jacob Berzelius first isolated this element from silica. He named it silicium, from the Latin silex, meaning flint. But back then, no one could have imagined that this gray steel metal would become the foundation of the 20th century's technological revolution. Pure silicon doesn't exist in nature. It's always bonded with oxygen, forming silicon dioxide, ordinary sand, quartz, rock crystal. The Earth's crust is 27% silicon. It's the second most abundant element after oxygen. Every rock, every grain of sand contains it. But turning this ubiquitous element into pure metal, that's a titanic task. The breakthrough came in the mid-20th century when scientists realized silicon could be a semiconductor. This meant it could conduct electricity better than an insulator, but worse than a metal, and that property could be controlled. That's how the idea of the transistor was born, and then the microchip. The first silicon transistor was created in 1954 at Bell Labs. From that moment on, Silicon Valley began, not just a place on the map, but an entire era. Today, global production of metallic silicon hits 9 million tons a year. China produces around 65% of all silicon, Russia about 8%, and Norway, Brazil, and the US split the rest. But this entire journey starts with one thing: sand. Not just any sand, but quartz sand, nearly pure silicon dioxide. It's mined in specialized quarries where silicon dioxide content exceeds 98%. The largest deposits of quartz sand are found in Norway, the US, Brazil, and Russia. Massive excavators scoop up white sand that looks like sugar and load it into dump trucks. This sand heads to a metallurgical plant where modern-day alchemy begins. Inside a giant industrial hangar sits a furnace that looks like a spaceship, an electric arc furnace. It stands 33 feet tall, 20 feet across. Inside, 3 massive graphite electrodes, each as thick as a telephone pole. When tens of thousands of amps surge through them, an electric arc forms between the electrodes, a miniature lightning bolt that hits temperatures of 3,600 degrees Fahrenheit. That's hotter than volcanic lava, hotter than the surface of some stars. Into the furnace goes quartz sand mixed with carbon, wood chips, coal, or petroleum coke. Carbothermic reduction begins, a chemical reaction where carbon rips oxygen away from silicon dioxide. The formula is simple, but the process? Pure hell. Silicon dioxide plus carbon at 4,000 degrees Fahrenheit turns into liquid silicon and carbon monoxide. The furnace roars like a jet engine. Inside, a fiery inferno rages. Molten silicon's heavier than slag, so it sinks to the furnace floor, forming a silvery lake of liquid metal. Every few hours, workers in fireproof suits open the tap hole, an opening at the bottom of the furnace, and molten silicon pours out in a blinding river of fire into special ladles. The stream's temperature? 2,700 degrees. The air around it shimmers with heat. Silicon gets poured into cast iron molds, where it slowly cools, turning into gray metallic ingots. This isn't pure silicon yet. This is metallurgical grade silicon, about 98% pure. It contains impurities: iron, aluminum, calcium. For metallurgy or silicone production, that's good enough. But for electronics, absolutely not. Microchips need silicon that's 99.9999999% pure. That means for every billion silicon atoms, there can be no more than 1 impurity atom. Reaching that level of purity is a task that borders on magic. Metallurgical grade silicon heads to a chemical plant where the purification process begins. The silicon is crushed into powder and mixed with hydrogen chloride at temperatures of 600 degrees Fahrenheit. This creates trichlorosilane, a volatile, toxic liquid that boils at 90 degrees. It's an intermediate compound, but it's critically important. Trichlorosilane passes through a series of distillation columns, giant towers as tall as a 10-story building. The liquid boils, evaporates, condenses, boils again, and with each cycle, impurities get left behind. After 100 cycles, you get trichlorosilane that's 99.9% pure. Now you need to turn it back into pure silicon. That's where the Siemens process comes in, one of the most beautiful and complex in metallurgy. Inside a sealed reactor, they install thin silicon seed rods. Purified trichlorosilane is fed in along with hydrogen and heated to 2000 degrees Fahrenheit. At that temperature, the trichlorosilane breaks down and pure silicon deposits onto the seeds, building them up layer by layer, atom by atom. The process runs for several days. In that time, those thin rods grow into thick cylinders up to 8 inches in diameter and weighing up to 660 pounds. They look like giant gray icicles. This is polycrystalline silicon, the purest material humans have ever made. Purity reaches 11 nines, 99.999999999%. A single kilogram of this silicon costs anywhere from 20 to 50 bucks, tens of times expensive than metallurgical grade. The polycrystalline silicon gets chopped into chunks and shipped off to single crystal manufacturing plants. Here's where an even more remarkable process begins: growing a crystal. Yeah, growing it, like a plant. Chunks of polysilicon get loaded into a quartz crucible and melted at 2592 degrees Fahrenheit, silicon's melting point. What you get is a mirror-smooth lake of molten metal. Then they slowly lower a seed crystal into the melt, a perfectly oriented piece of single crystal silicon. And they start slowly rotating it while simultaneously pulling it upward at a rate of a few millimeters per hour. The molten silicon crystallizes onto the seed, atoms locking into a perfect crystal lattice, copying the seed structure. The process is like pulling a giant sugar thread from syrup, except instead of syrup, it's molten metal at nearly 3000 degrees Fahrenheit. After several days, a cylindrical single crystal grows from the melt, an ingot up to 6.5 feet long and about a foot across. It weighs up to 660 pounds. This is one continuous crystal where all trillions upon trillions of atoms are arranged in perfect order. This cylinder is called a boule, or ingot. It's gray, smooth, with a metallic sheen. One of these ingots costs tens of thousands of dollars. The boules are sent for cutting. They're clamped into special machines and sliced by diamond saws into thin discs, wafers. Each wafer is about 700 micrometers thick, less than a millimeter. Cutting moves at a few centimeters per hour because the slightest vibration will shatter the fragile crystal. A single boule yields several thousand wafers. Each wafer gets ground and polished to a mirror finish. The surface must be absolutely flat, deviation no more than 1 nanometer across an area of 12 inches. That's like leveling a football field to within the thickness of a human hair. These finished silicon wafers are the foundation of all microelectronics. Photolithography imprints circuits onto them, billions of transistors just a few nanometers in size. A single 12-inch wafer can hold up to 1,000 processors or tens of thousands of memory chips. After etching, doping, and depositing metal contacts, the wafer gets diced into individual chips. Each chip is a complete microprocessor, ready to become the brain of a smartphone, computer, or car. The entire journey from sand to processor takes several months and passes through dozens of factories across different continents. This entire incredible journey, from a handful of sand in a quarry to a microscopic chip in your phone, shows how far humanity has come in understanding matter. Silicon gave us computers, the internet, artificial intelligence, spacecraft. Every day, 7 billion people hold devices in their hands that work because of this element. The global silicon wafer market exceeds $15 billion a year, and the microchip market, over $500 billion. All of it built on that same gray metal that was once ordinary sand. Silicon became the foundation of the digital era. Without it, there'd be no computers, no smartphones, no internet. We live in a silicon civilization without even thinking about it. And every time you touch your phone's screen, remember, beneath the glass, billions of transistors are working, made from that very same sand you walk on every day.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace. Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock? To do this, it's sent to a heating furnace where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder. And the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides. Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide. And the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision, then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.